Okay, so now we want to do this integral. Let me sketch the region. It's similar to the one that we just did. So this is in the first quadrant. X equals y squared. This is like this part of the y equals square root of x. And then x equals 1 minus y squared. It looks something like this. To find that intersection point, we need to set y squared is equal to 1 minus y squared. That'll give us the y coordinate. And if we solve this, notice that if we just solve this equation, we get two solutions, but we only want the positive solution. So this is just 1 over the square root of 2. Now, to determine which order of integration, notice that if we do the x integral, we're going to have to go from this curve to that curve. Or sorry, if we do the y order of integration, we're going to have to go from y equals 0 to this curve when x is to the left of 1 over the square root of 2, and when it's to the right of 1 over the square root of 2, we're going to have to go from 0 to this curve. So we'd have to split it up into two different integrals. But if we do the x integral on the inside, x is always going to go from this curve to that curve no matter what y is. So x integral on the inside, x goes from y squared to 1 minus y squared, and y goes from 0 to the y coordinate of that point, which is 1 over the square root of 2. X dx dy. If you look at the inner integral, this is y equals 0 to 1 over the square root of 2. The antiderivative is x squared over 2. So this is 1/2 1 minus y squared squared minus y to the power of 4 dy. This is a Calc 1 integral, and it is equal to 1 over 3 times the square root of 2. It's a tedious Calc 1 integral, but it is a Calc 1 integral.